Yeah, so another problem we are going to solve is this one. RS. So this is one circuit. So this is a feedback system and this is without the feedback system, right? Only the forward path is there. We are saying in the following systems, if the forward path gain is reduced by 10% in each system, okay? So forward path gain, let's call it GS, is reduced by 10%, okay? Then the variation in C1 will be, and C1 and C2 will be, okay, so this is C1, this is C2, okay? So there are these two circuits. Now if you have a 10% reduction in GS, right? So here there is no feedback path, right? So GS is directly 16 into 3, 48. So if you reduce it by 10%, your gain is basically reduced by 10%. So the output will also be reduced by 10%, right? So there is no catch here, right? Because here the CS transfer function is just this gain, right? But here, what is the transfer function? Here the transfer function is 10 by 1 plus 10, right? And this was your forward path gain, right? Now if this one changes by so this was the original transfer function. Now let's say this has reduced by 10%. Basically it has become 9 now. So 1 by 1 plus 9. So earlier it was 10 by 11. Now it is 9 by 10, right? So what's the percentage change? So I'll show two approaches to solve this. This is approach one where these values are given, right? When it is given, it's easier. But let's say in generic case, instead of 10, they have given G, right? Then how would you solve it? So first let's solve in this way, right? Approach one. Yeah, so this is your new T dash after the reduction in GS. So what's the percentage change? Percentage change would be T dash, basically, yeah, T dash S minus TS divided by TS, right? And you want it in percentage and you multiply by 100, right? So what's this? 9 by 10 minus 10 by 11. So you can do this, right? This by this is 9 by 10 divided by 10 by 11 minus 1 into 100, right? So 99 by 100 minus 1, 100, basically minus 1%. Yeah. So in the feedback system where there is feedback, although there is change in 10% in the forward loop gain, forward path gain, but the impact in overall transfer function is only 1%, right? So that's the use of the feedback path, to stabilize the system, so that if there is some change in the transfer function, the overall transfer function is not impacted much. Yeah, so now let's see the approach 2, right? This is approach 1. What we can do, let's say if there was no value given, right? Because actually we don't need this value to arrive at that solution. So let's say it's given in terms of G, right? And later we'll replace that G. Then what's the transfer function? G by 1 plus G, right? Open loop gain is 1 minus G, so this becomes 1 plus G, right? So we are trying to find out delta T, okay, when there is change delta G. So you take a derivative of this, which becomes 1 plus G whole square in the denominator, 1 plus G dG minus G and then dG, right? So this will become 1 by 1 plus G whole square. This will get cancelled out, right? So this is the delta T. Now we need to find the percentage change, right? So delta T by T we need to find. So delta T by T would be this guy divided by this guy. So it will be 1 by 1 plus G square to 1 plus G by G. So this will be 1 by G into 1 plus G. Delta T by T is this. Okay. Yes. So what was the value of G? So if you plug it here, right? Earlier it was 10, right? 1 by 10 into 11. So this is the ratio. If you want in percentage, you have to multiply by 100. So this is approximately, as you can see, 1%, right? 100 by 110 is coming. It's fine. So this is one quick way to arrive at the solution.